So law of sines, we just need to set them up like what we did yesterday. So we're going to go opposite sides. So because we're solving for a side length for the first one, I want to put the side lengths on top. So I'll say b over sine of 33 degrees equals 24 over sine of 108 degrees. That's how I'd set up something like problem 1. And then I multiply both sides by sine of 33 degrees. And my exact answer should be b equals 24 sine 33 over sine of 108. For problem, I'll put the approximate answer in a second here. Problem 2 looks like this time we're using angle B, but we're solving for the angle measure instead. Find the measure of angle B. So we would set up sine of B over 23 equals sine of 35 over 45. And then for this one, we're going to need to use inverse trig functions to solve it. So we're going to multiply both sides by 23, and we're going to get 23 sine of 35 over 45 equals sine of B. And then we'll get some weird decimal answer, and we take the sine inverse of that decimal answer. And it's going to look like that. So B equals sine inverse of this. Now, for problem 1, what did we get for our B value? I don't have it written right in front of me, but what did we end up getting for that one? Anyone get that one? You can type it into the chat for the B. Let's see, I think I do have it written down somewhere. Here we go. Problem 1, 13.7. Rounded to the nearest tenth, so 1 decimal place. Problem 2, the B value, 17 degrees. Is that right? And that makes sense. It was rounded to the nearest whole degree. And because the side length is 23, it should be smaller than the 35 degree angle. So I got the measure of angle B equals 17 degrees for problem 2. All right. For problem 3, setting up the law of sines. Hopefully shouldn't be too difficult now that we're back into the swing of things. We're solving for side C this time. C over sine of 23 degrees equals, and then 15 over sine of 77 degrees. That's what we'll end up with for this one. Now we multiply both sides by sine of 23. And we get 15 times sine of 23 equals sine of 77. And then that solves for side C, which in this problem comes out to 6.02. Rounded to the nearest hundredth, which is 2 decimal places. All right. And the last one, part D here, or number 4 here, we're looking for the measure of angle EDG, which is this whole angle here. So essentially we've got this triangle here that looks like this. It's got a side length of 30. There's side C, there's angle E, and then here's EDG. And then we've got another triangle that looks like this. It's going to have side angle F, 125 degrees. It's got a side length of 20, a side length of 30, angle G, and then this is angle FDG. I think that's the best way to write that down. Kind of looking at 2 different triangles here. And we want to use the law of sines, and the way it would work is first we're going to end up actually finding angle G, because that's opposite this 20 degree side, and angle F's opposite the 30 degree side. And what happens is when we find angle G in this triangle, we're actually going to find angle G in this triangle as well, and then we'll have 2 angles out of 3 for angle EDG. So we kind of have to work through the first triangle to find the angle measure for the second triangle. So I set up my trig function here. I'm going to say sine of G over 20 equals sine of 125 degrees over 30. Multiply both sides by 20. 20 times sine of 125 degrees over 30. And then take the inverse of both sides. And we're going to get our angle G measure. Anyone know what we get for a measure of angle G? Just round it to the nearest whole degree, since that's what we're asking for right now. Anybody have that? I don't have it written down anywhere, so that's what I'm asking.
33.
I'm sorry, what'd you say?
33.
33. Okay, perfect. 33 degrees. That sounds right. So 33 degrees. So what happens is we have a 33 degree angle here as well. And that means we have two angles out of 3 of this right triangle. So we can say 180 minus 90 is 90. 90 minus 33. And we'll end up with 57 degrees. So that's how we found this angle right here, 57. So we can say the measure of angle EDG is 57 degrees. All right, that would be that'd be our result for number 4. So we can still use law of sines, and it's going to help us ultimately get to the answer we're looking for. It's just going to take a little bit longer. All right, any questions on those first 4 problems for us today? No? Okay, good. So today we're going to talk about something called the law of cosines. So it can be derived from an obtuse triangle by using the altitude of the triangle. So the altitude is when we're drawing a line from a vertex that's perpendicular to the opposite side. All right. And it's from the vertex of the obtuse angle specifically. So obtuse angles, that's important to know. Anyone know what an obtuse angle is? What the definition is?
Bigger than 90?
Exactly, an angle greater than 90 degrees. All right, versus an acute angle, which is an angle less than 90 degrees. So yeah, that would be an obtuse angle. All right, so what we're going to be talking about today is this law of cosines using an obtuse angle. It is important to know obtuse versus acute, by the way, just because that vocabulary could be on the quiz on Friday. We're going to have a quiz on Friday that's going to be on law of sines, law of cosines. So just to give you a heads up, you might want to write this down if you haven't written it down yet. Because remember, we have open notes, so that's useful to have written down, just so we know what an obtuse versus acute is. All right, so let's look real quick at law of sines. If I give you any triangle, like let's just say here's triangle ABC, and then side ABC, and I say let's say side C is 87 degrees, is 87 centimeters. Angle A is 52 degrees, and angle B is, or side B is, let's see, 82 centimeters, something like that. We're just making up these values. And I say, let's solve for A, side A. Well, we'd say, okay, let's do law of sines. We'll say A over the sine of 52 degrees equals, let's do B, 82 over sine of B. Well, that's not going to work because I don't have an angle B yet. So we'll have to use angle C then. A over sine of 52 equals 87 over sine of C. Well, that's not going to work either. So I was given 3 pieces of information here. I was given 2 sides of the triangle and 1 angle in the triangle, but I can't use law of sines to solve for it. So this is where the law of cosines comes in. It's because the law of sines is not always going to work. In this situation, the law of sines won't work. So the way the law of cosines works is it starts with a triangle that looks like this. Say we have this entire length here is side length A. And then over here we're saying that this side is going to be X and the other side is going to be whatever is left, A minus X. All right. So what we would do with this is if we're looking at two specific right triangles, like let's say here's our first right triangle here. All right. And if we were trying to solve for this triangle, we would say x squared plus h squared equals c squared. We can use the Pythagorean theorem to solve for it. The one common side that both of these triangles have is h. So I want to get h by itself in the equation. So I can say h squared equals c squared minus x squared. That would be a great way to represent this equation in terms of h's. And I'm going to try and do the exact same thing for the second triangle here. And again, h is the shared side, but I should be able to set up the equation still and say h squared plus a minus x squared equals b squared. And then I can say h squared equals b squared minus a minus x squared. That's how I would set this thing up. Those are my two equations. And what happens now is I technically have h in terms of two completely different equations. I have h squared and h squared. So one of the equations says h squared equals c squared minus x squared. The other equation says h squared equals b squared minus a minus x squared. So now I'm at the point where I just want to simplify as much as possible here. So I have the Pythagorean theorem relating these two triangles, and I'm trying to make it one equation right now. So the a minus x squared can be rewritten as a minus x times a minus x. So that's a squared minus xa minus xa, so minus 2ax plus x squared. And the other side of the equation we'll leave right now is c squared minus x squared. Now I have a negative that I need to distribute. And that's going to change all of the signs on the left side of the equation. The right side of the equation, meanwhile, is just hanging out right now. And this becomes b squared minus a squared plus 2ax minus x squared. And then I can go ahead and, let's say, add x squared to both sides. And that's going to get rid of x squareds, actually. It simplifies the equation a little bit for us, which is nice. So I'm left with c squared equals b squared minus a squared plus 2ax. Now, just looking at this, c squared equals b squared minus a squared plus 2ax. If I covered the 2ax up and just said, let's not look at this right now, what's that look like to us? C squared equals b squared minus a squared. What's it kind of remind us of? It should look like an awful lot like the Pythagorean theorem, right? Except we have this plus 2ax. But yeah, very similar to the Pythagorean theorem. All right. So what happens now, I have this side length here, c squared equals b squared minus a squared plus 2ax. And I say, let's go ahead and say we want to find side length b specifically. So we're going to focus on angle B and side length B here. So what we would do is we would say, let's go ahead and get the b squared by itself on one side. We're going to subtract 2ax from both sides. We're going to add a squared to both sides. So we get a c squared plus a squared minus 2ax equals b squared. We're just rewriting this equation a different way. So it's c squared plus a squared minus 2ax equals b squared. Now, if I'm looking at angle B here, and I'm thinking about this from a cosine perspective, like if I want to use the cosine function, I would use the adjacent side and the hypotenuse of the triangle. So I could say cosine of B equals adjacent over hypotenuse. Remember, cosines only work with right triangles, so I can use it on this small right triangle here. And I'm essentially going to solve for x. I'm going to get c on the other side of the equation. I'm going to get c times cosine of b equals x. And what this is going to allow me to do is it's going to allow me to take this equation and plug in for x so I can get rid of an x there. So now I can write this as c squared plus a squared minus 2a times c cosine of b equals b squared. And that allows me to get rid of the x, and now everything's in terms of a's, b's, and c's. And that's good because this whole triangle is side length a, side length b, side length c. That's exactly what I want. I don't want any x's or y's or anything like that. So this is an equation for the law of cosines. It looks kind of weird, kind of intimidating, but let's go ahead and look at it down here when it's all cleaned up. This one that we just found is actually the middle equation here. B squared equals a squared plus c squared minus 2ac cosine of b. And that would be this side right here where it's saying, hey, if I do cosine, I'm using the two adjacent sides, all right, which is side A and side C, to solve for side B. That's why it's b squared equals. If I used a different one, like a squared, I'm solving for side A, and that means I'm using side C and side B, and I'm using angle A to solve for it. And then finally, the last one, if I was using angle C, I'm using sides B and sides A to solve for side length C, and that would be this equation. So it doesn't matter which one I have, the equation is going to be very similar. It's going to be using the two adjacent sides to that angle to solve for a missing value. All right. And it's important to note that the law of cosines does not work in every situation when solving for a missing side or angle of a 9-right triangle. But when can you use the law of cosines? You can use it in two situations. The first one we already looked at is if I gave you, let's say, triangle ABC, and I gave you this side was 82, this side was 87, and then I gave you an angle here that was 52 degrees. That's one situation where we'd use it. Another situation where we'd use the law of cosines might be where I give you a triangle, let's say ABC like this, and I give you all the side lengths, let's say 12, 15, 24, something like that. That would be another situation where I would use the law of cosines, where I'm given three side lengths and I can find a missing angle. And we'll talk about that in a little bit, because right now all of these equations are set up to find missing side lengths. Okay. But I can actually use the law of cosine to find a missing angle if I'm given three side lengths of a non-right triangle. And we'll talk about that in a few minutes. But it could be either one of those situations or when I'm going to use the law of cosines. If I have any other situation, typically with triangles, like let's say, I'll give you triangle ABC here, and we'll say angle C is 38 degrees, this side length is 12, and this side length is 15. Well, I can use the law of sines here because I have the opposite side and opposite angle, and then I can use side and angle right there. So this would be a law of sines problem, not a law of cosines problem. So the law of cosines wouldn't work because it's not set up properly for it, but that's okay because I have the law of sines, and I think the law of sines is easier anyway, so I'd rather use that. All right, let's go ahead and set this up and take a look at using the law of cosines now, though. So for this first problem, it's the situation that I just showed with the black triangle directly above. We've got two side lengths and an angle. The angle is 105 degrees. So setting up the law of sines, we're going to solve for the missing side. The missing side here is lowercase a. And the variables really don't matter because what's going to happen with the law of cosines is we have the other two sides squared and summed together. And then minus 2 times the lengths of the other two sides times cosine of angle A. So the sides are, 21 and 15. And the order doesn't even matter on these, which is really nice because of all of the multiplication. So we don't have to be too terribly careful as long as we get the right side lengths listed. And we get something that looks like this. 21 squared plus 15 squared minus 2 times 21 times 15 times cosine of 105. Now I'm just going to go ahead and say let's break this into parts. And we'll do this first part here, 21 squared plus 15 squared. That comes out to 666. And then the second part, 2 times 21 times 15 times cosine 105 comes out to negative 163.05 when I plug that into my calculator. So I end up getting a squared equals 666 minus a negative 163. That's actually going to add up 829.05. And then I square root both sides to get side length A. A equals 28.79 centimeters. And we'll round to the nearest hundredth here. So side length BC is 28.79 centimeters after I do all of that. All right. That's how I would use the law of cosines to find a missing side length. Okay. There's one more practice problem here. If you guys want to, go ahead and try it out. Try the other problem real quick. See if you can get it set up, looking for that missing side length A. So we'll be using the exact same formula. So see if you can set it up and solve for it real quick. I'll write it down here in just a second, but go ahead and give it a try first. All right, so for that second one, setting it up and then just running it through your calculator, I ended up getting 8.7 centimeters for side length A. Okay, and that makes sense. 35 degrees is kind of a small angle, so this is saying that 35 degrees is going to be the smallest angle in this triangle. That's one thing to keep in mind when we're solving for these problems is shortest side lengths are always going to be opposite the smallest angles. Longest side lengths are always going to be opposite the largest angles. So one thing to keep in mind, so like when we looked at problem A, angle A was 105 degrees, so it makes sense that side length BC, or side length lowercase a, was longer than the other two side lengths. So our work checks out for the first problem. It's always a good way to double check and make sure we're doing it the right way there. All right. Any questions so far on that, on the law of cosines so far? Okay, good. So the last thing today then, pretty straightforward, is these inverse trig can also be used with the law of cosines. And that's saying we can find a missing angle measure if we're given all three sides, which is the other idea I showed up here with the blue triangle. So what happens if we have an equation, let's just take one of them, for example, the first one, a squared equals b squared plus c squared minus 2bc cosine of a. And we want to solve for cosine of a, get that by itself. The good news is we'll never be asked to do this, but it's already been done for us, which is kind of nice. So we get a squared minus b squared minus c squared equals negative 2bc cosine of a. And like I said, it's already done up here. I'm just showing you where this comes from. Now I divide everything by negative 2bc. And what happens is this negative here is going to affect the numerator, because I have this a squared minus b squared minus c squared. Distribute that negative through, and it's going to make this a negative a squared plus b squared plus c squared. So what ends up happening is I end up getting b squared plus c squared minus a squared all over 2bc. That equals cosine of a. And that is what we have up here. So that's where these equations come from. If we change each one of them around respectively, we're going to end up with a cosine of a, cosine of b, cosine of c. And then we would need to do some inverse trig to solve for that missing angle measure. And that's how these problems would work. So for this particular problem, it's to solve for the measure of all angles using inverse law of cosines equations found above. So let's start with A. Since we already have that one, we just showed how to do it. So if I'm looking for A, I'm going to say let's do cosine of A equals, and then we're going to use the side lengths B and C. I'm just going to put them in quotations here. This is side length B, side length B, C, and side length A. So it's going to be B squared, so 14 squared, plus C squared, 12 squared, minus A squared, 18 squared, all over 2 times B times C. So the numerator is 14 squared plus 12 squared, and then minus an 18 squared. It comes out to 16 in my numerator. My denominator, 2 times 14 is 28. 28 times 12 is 336. So that's what I end up getting for cosine of A. And I still need to go ahead and do my inverse cosine. Take the inverse of both sides. And I get A equals cosine inverse of 1636. And then go ahead and throw that into my calculator. And I'll get measure of angle A equals 87.27 degrees. Well, we're on to the nearest hundredth here. And that makes sense, again, because 87.27 is almost 90 degrees, and it's opposite the longest side of the triangle. So it makes sense that it's pretty close to 90 degrees. It's going to be the largest angle of this triangle. So measure of angle A, 87.27 degrees. Okay. Now, once I have that measure there, I could technically use the law of sines from here on out. I only need to do the law of cosines one time, because I could technically say, hey, let's find angle B. We'll do sine of B over 14 equals sine of 87.27 over 18. And I could find angle B that way. That's one way I could do it. But for today's sake, I'm trying to use the inverse law of cosines. So I'm not going to use that method right now, but I could. Instead, I'm just going to go ahead and do angle B here. So cosine of B equals C squared, 12 squared, plus A squared, 18 squared, minus B squared, all over 2 times A times C. 2 times 12 times 18. And I still say it goes pretty fast. We just have to make sure we're putting it into our calculator correctly. So I get 272 over 432. And then I go ahead and do the inverse cosine of both sides to find my angle B measure, my measure of angle B. All right, so I mean, I still think law of cosines, it works. I think law of sines would be faster, but I'm just showing you another law of cosines example here for an angle measure. And this one came out to 50.98 degrees. And now we've got two angles solved for in a triangle. To find the third angle, I don't need law of cosines, I don't need law of sines. I can just do a 180 minus at this point. 180 minus 87.27 minus 50.98. And put that into my calculator. I end up getting 41.75 for angle C. All right. So that's how I find missing angles using the law of cosines. So that covers everything for today. Actually, we went pretty fast.